technology, and the Navy quit running a lot of their own standards, and so they started trying to use commercial standards. And, you won't find an ASTM standard. ASTM standards are books like this. This is the book on shipbuilding, okay? Ships and marine technology, okay? Now I happen to have the 1998 version in my office. I actually have a shelf like this of ASTM standards. The steel standards are about that thick, okay? There's 7 or 8 volumes. And it's actually '01. The first set of ASTM standards 100 years ago were basically steel standards. Now they got them for insulation, anything you can think of. They have ASTM standards. And the entire shelf, if you had a full set and you got to buy them each year, would probably cost you $50,000 or $100,000. It would take 20 feet. They'd probably go along that whole wall. However, if you just Google an ASTM standard and you're an MIT registered user with the libraries, it will pop up even after you Google. The computer, at least my computer now over the last 6 months, will sense that I'm looking for an ASTM standard, and I'll get a pop-up window that says, would you like to download this for free from the MIT computer? Actually from Compass. MIT libraries own, they have to, that's what part of your tuition goes for, is maintaining the libraries and stuff. And so we have these books of standards, and I have some of them because I use them fairly often. I mean, here's a standard, F 1116, what is this? 66. Wow, it's a long one. Most of them aren't this long. Guys, gloves. Okay. Human engineering design for marine systems, equipment and facilities. Okay, fine. I got a standard for human engineering among ships and shipbuilding. There are other standards, such as, and I would have gone through, but I decided I didn't use hydrogen cracking. But there's the structural welding codes for steel, which is every bridge and building in the United States is built to this code because virtually every state in the United States has incorporated this into their building codes. You cannot get your building certified because this doesn't have force of law. It's made by the American Welding Society by a committee, but it was adopted by every state into their building codes. That gives it the force of law once the government approves it. And all your OSHA standards and things like that usually are calling out standards like this. I actually have a module in this course on codes and standards and whether they're good or bad for innovation. Okay, but then ASTM will. I just got this one because I get things for free from the American Welding Society because I grade their welding engineer exams, but for free. Well, this is what I get for grading them. I get a $1,200 a year with free books, which cost them next to nothing. Okay, so all 60 standards referenced by AWS in the structural welding code are now compiled in here. So this is the second edition, and this is just all the ASTM standards for the structural welding code for steel. Just the structural welding code itself takes up about this much space because there's one for aluminum, there's one for titanium, there's one for stainless steels, there's one for repair welding. They make money off these codes. Okay, used to be 30 years ago, you could buy one of these for $75, $400 now.
Wow.
Okay.
Gas also costs like 10 cents back. That's cost inflation.
No, I remember gas costing 25, and that was back in the late 50s. Okay, 25 cents. But no, the codes and standards. I can show you some X-ray radiographs in the lab. That I buy from ASTM, which are actually radiographic, film, and I bought those 15 years ago for $300. Today it's $1,500. Over the last 20 years, the professional societies who sell the standards have determined this is a great money-making tool, okay? If I went back 20 years ago, the American Welding Society, before they started collecting money for certifying welders to get a welder has to be certified, you talk about certification and decertified for the titanium. You can be certified, not for the Navy welding, but for commercial welding, you can be certified by the American Welding Society. They started in the mid-90s. Their total assets, which they publish in the Welding Journal once a year, back then were about $2 or $3 million. They just published it last month. They're worth $100 million today. 20 years later, you know, they're making $5 million a year off certifying welders, nationally and internationally. They certify welding engineers. Now, they don't certify as many welding engineers as they do welders, but I grade all those exams, okay, as far as that goes. And I'm charging them, I just get some standards from them. But anyway, you can't build anything without standards. You know it. You have to go to all the Navy standards and, you know, specifications and qualifications. You can't even turn a valve on a ship without looking it up in the book, right? Because you turn the wrong valve, you could kill a few people, okay? So, I'm just going to do a little catch up on a few things here. This is something in the stainless steel lectures. I'm just going through see what I missed when I was going through. This is molybdenum content. I told you put the molybdenum in stainless steel for chloride corrosion resistance. This is the critical pitting temperature. At what temperature can you get rid of pitting problems? And here's 316 stainless steel, 317, which is kind of the medical grade. The L versions, and L versions are a little bit better because they don't form these carbides. AL6, okay, this is what the Navy wants to make submarines out of, and you can see why. The ocean can get to 30 degrees centigrade in the tropics, okay? And if you made it out of some other stainless, you'd end up hitting your submarine. Okay? So that's why they have to add that much molybdenum. They looked at it, and I think they've given up on it now. But that was something of 10 or 15 years ago. It was the all stainless steel submarine. They had given up on the titanium submarine before that, but they spent worried about that for a while. If you're going to weld, this is the Shaffer diagram that I put up yesterday. The Shaffer diagram, basically tells you when you have low chrome, low nickel, low alloying, applied chrome nickel. Down here, you just got a carbon steel, okay, ferrite and martensite. And then over here, if you got a lot of chrome, you'll be ferritic stainless. If you've got a lot of nickel, you'll be austenitic up here, face center cubic, body center cubic. Here's where your 304 or 309 is a weld metal, a little more richly alloyed than the 304 garden variety. 310 is very richly alloyed up here. If you're trying to weld dissimilar materials, I mean, I talked about welding the chrome moly steel boiler tube to the stainless steel boiler tube for that destroyer back in 1978 or 79, whatever it was. When you're mixing those metals, you're going to get something in the weld metal that's some combination of the weld metal electrode and the base material, and you're going to get dilution. And if you're diluted very little, your weld metal is going to have a composition that's mostly weld metal, the electrode composition. If you dilute a lot, you're going to be down here like the base material. Well, obviously, you can get martensite if you don't do this properly. And it turns out, my example on that is, it was 30 years ago, I had a student working at the Army Research Labs over here in Watertown, and he was working on hydrogen cracking of steels, because the Army welds armor steels. And he called me up. The State Department was all over the U.S. Army because they had agreed to sell the Egyptians some tanks. So these tanks were being built in Lima, Ohio. Anybody from Ohio? This is Lima, like Lima bean, okay? But Lima, Ohio is where the U.S. Army's tank plant is. This is where they were building Abrams tanks, the MG tank, okay? And I don't know if they were building Abrams for the Egyptian Army. They were building some older tank model of the U.S. But they were having some problems. And I told you when the Navy started welding the Nautilus, or one of the first nuclear submarines, they basically couldn't solve the hydrogen cracking problem, so they used austenitic stainless steel filler metal. And that's because the austenitic stainless steel will dissolve 10 times the hydrogen and is 10 times more resistant than carbon, the ferritic steel weld metal. So they're having some problems welding this, so they decided to weld the Egyptian tanks with austenitic stainless steel weld metal. Okay. Only they didn't worry about how much dilution, and depending on the weld metal they were using, they were getting cracking. Okay. And here's the martensite boundary. If you compare it with this one before, you can see this is martensite, this is austenite martensite, this is austenite. So somewhere in here is some martensite boundary. And all this guy's doing is showing if you're welding dissimilar metals like armor steel, which is going to be down here somewhere, with a stainless steel, if you don't have the right amount of base metal melted to weld metal melted, you're liable to get martensite, extremely high hardness, very susceptible, essentially impossible not to hydrogen crack it, even with just the residual hydrogen that's in the steel to begin with. You're screwed, okay? So he calls me up at 6 o'clock in the morning. Oh, the State Department is complaining because we're welding Egyptian tanks and we're shipping them to them full of cracks. You know what? If you're going to sell weapons to your enemy, you might as well sell them defective ones, right?
I'll paint over the cracks.
Yeah, paint them over. A little epoxy.
Polyfill.
Yeah,
Not even epoxy.
duct
wood
tape.
glue.
Name it, okay? The Egyptians weren't happy, the State Department was embarrassed, okay? The State Department should be embarrassed. Okay. So another story on stainless steel, which I brought this before, and I kind of showed you before, but anyway, so this is a Farberware pot, okay? This is probably 20 years old. Farberware came to me because of the MIT Industrial Liaison Program. They were members, and you can get free consulting from an MIT faculty member for about an hour if the faculty member says yes. So in the 1980s, I actually did more than any other faculty member at MIT. Just like I told you, I did a lot of failure analyses. I used to have companies 3 or 4 hours a week. 3 or 4 companies coming in. What's your problem? They tell me their problem, and I shoot from the hip, just like I do around here. Okay, I haven't changed. Okay, so Farberware came in, they brought this pot with them. And they said, well, we're making these stainless steel pots. It's 304 stainless steel, garden variety stainless steel. It's got aluminum on the bottom, and that's an interesting story too. But we shipped some of them to Japan, and when they show up in Japan, they got cracks in them. They didn't have cracks when they left. So I went and got my magnet, and I said, see the difference? And they were sort of amazed. Well, if you know anything about 304 stainless steel, which they didn't, they were coming to find out about the metallurgy here. Huh?
Which they didn't, idiots.
Well, they were making stainless steel pots. I mean, why didn't they know about this? Turns out 304 stainless steel, when you stretch it, you can have martensite that you can get by quenching and changing the temperature, but you can also get martensite from the austenite in 304, which is actually metastable. You have to know that. And when you stretch it and deform it, it will transform by strain-induced martensite. And so when you take a piece of flat disc of stainless steel and punch it into a forming die to make a pot out of a flat disc, you're getting more deformation at the top than you are at the bottom. Hey, the very bottom gets no deformation. It starts out as a circle and it ends up as a circle. This stuff gets bent. Well, big deal. It's just kind of a 90-degree bend. This stuff actually gets compressed and stretched. And basically, the magnetism is a function of how much deformation is in the stainless steel. this is partially body-centered tetragonal martensite. This stuff is not susceptible to hydrogen cracking, this stuff is. Okay? So I said, well, so I explained that this is why it's cracking. It was delayed cracking. How did I know that? Well, when they put it on the boat in New York, the manufacturing sites in Brooklyn, okay, and get it to Tokyo, it didn't have cracks, and then it did have cracks, a week and a half or 2 weeks later, and that's a delay. I figured that out myself, okay? And so it was just cracking on the boat. It was delayed cracking, so I knew, well, the only thing that causes delayed cracking in steels that I know of is hydrogen. So then I had to figure out, well, where do they get the martensite? Well, I knew that because I knew about strain-induced martensite in 304. But I said, I don't know where you're getting your hydrogen. Just start out with a sheet of 304. Where'd the hydrogen come from? And they said, well, do you think it has anything to do with the fact to get good bonding of the polymer coating on the inside? They would take stainless steel powder and they would plasma spray it on the inside to make a very rough, porous surface that they could then impregnate the plastic inside, and then it would stick really well. And they were using argon 5% hydrogen as a gas for plasma spray. I said, yeah, that could do it. So problem solved, and since then I've had this little toy.
That's afterwards. So that's after all the heat stress, the heat's gone away, right? And then they're just gonna spray some hydrogen on top of it?
Well, it gets hot when they, the plasma spraying metal powders on the inside.
So plasma spraying, what does that mean?
Plasma spraying, they take stainless steel powders, they put them in, they have a plasma torch, like an arc welding torch, and they inject the powders into the flame of the plasma, which is 5% hydrogen,
Okay.
which is now hydrogen atoms.
So it is super hot.
Oh, 10,000 degrees Kelvin. Yeah,
Okay.
it's pretty hot.
Not melting. Love that.
No, not if you go fast. I can run my finger through a candle. I've done it through a welding arc, plasma flame. I go fast. Hey, my mother did that. But no, if you go quickly, you're not gonna overdo it. It gets hot, but it cools down quickly too, traps the hydrogen. They make it, put it in a box. It might have even cracked before they knew. They got out, it left the dock, but it was inside a box. It was packaged up. The cracking occurred within a week, okay? And in fact, these cracks have gotten longer over time because you got the residual stress. Where did the stress come from? There's residual stress in the forming of it, okay? You're gonna have stress, hydrogen, and a susceptible material. The original material wasn't even susceptible, okay? But once they formed it, it was. Okay, then the stress comes from the forming operation. I got a all expenses paid trip to the Faberware plant to look at other problems. And I show up. I show.
You saved them millions.
Oh, I did. So and they paid me a couple $1,000 as a design. A bit more. I don't remember. It was 20 years ago, so my rate was probably $150 an hour back then. Anyway. So you show up in Brooklyn. This is not the nicest area of Brooklyn. This is sort of an industrial area of Brooklyn. And you can kind of tell because the cab driver dropped me off and he sped away. Okay? And I looked around. And it was just after Christmas, as I remember, and there was snow all over the ground, on the sidewalks and everything. And I go up, I didn't know which side of the building, I just had an address. So the cab driver dropped me off. I go to the door and it's bolted. I mean, it's really bolted. And there's no real windows in this building either. And it's a city block size, okay? It's a factory city block size. So I start trudging through about 3 feet of snow on the sidewalks, which snow in New York is very clean. And I go literally, I didn't know which side to go. I went more than 3/4 of the way around the building before I found a door that wasn't completely bolted shut, okay? I could tell this was not necessarily a great neighborhood, okay? Finally, I found a door that you could knock, you could get in, and I went in and saw the plant. But I had another example in New York City once of, anybody know the George Washington Bridge coming into New York City? So the George Washington Bridge You come over the bridge and then it goes underneath the highway, the other highway, right? And so one time there was this 30 or 40 story building. This is just kind of a throwaway right now, we're just finishing up. 30 or 40 story building that was actually an apartment building. And they said, oh, we got a crack in the beam. One of the structural beams, 10 feet tall, web, holding up this 20-story building. And this is the beam that if you were driving through the tunnel, you know, you'd look up and that would be the beam that's holding up the building. And I got a crack. I said, well, how big is the crack? 9 feet. Oh, we want you to come look at it. So they give me an address. I don't know the neighborhood. I'm not from New York. I get a taxi, and the taxi again speeds off out of this neighborhood. I look down, there's all these little capsules on the side. I start looking around. Everything's bolted up. And I go and I knock. We can tear the TV out. I go and knock on the